Hi, everybody. We are going to talk about how to compare linear versus exponential functions today. So it's important as we kind of work through all of these new functions to look back and compare how they differ from ones that we've learned about previously. So that's why we're going to compare linear and exponential today, just so we can get an idea of the different characteristics and how we can tell one versus the other. So if you read through the top, it says linear and exponential functions share many characteristics. This is because they are based on two different but similar sets of principles. Linear functions are based on repeatedly adding the same amount. So if you think back, when we say repeatedly adding, that means that there is a constant rate of change, that slope. That means that it's increasing at a constant rate. Where exponential functions are based on repeatedly multiplying by the same amount. So very similar concept. Instead of it being something that we're adding or subtracting every time, it's something that we're multiplying by every time. So we're going to just first compare two tables. And so it says for exercise 1, the two tables below represent a linear function and an exponential function, which is which, and explain how you arrived at your answer. So if we look at table 1, really what we want to see is how is that y value increasing? So if I start by saying, okay, well 5 plus 5 is 10, but then I have 10 plus 10 is 20. So right away I can see that this would not be a linear function because my y value is not increasing at a constant rate, meaning it's not adding the same number every time to get to the next number. So when I see that, I think to myself, okay, can I be multiplying by the same amount? Well, so if I think about that, 5 times 2 is 10, 10 times 2 is 20, 20 times 2 is 40, and 40 times 2 is 80. So I can see that this must be an exponential function because I'm multiplying each of those numbers by 2. Okay, so let's say it's an exponential function. And I'm going to say because each output is multiplied by 2. And I'm going to say to get the next output. Okay, so that means table 2 must be linear, but let's see. So to get from 8 to 11, I'd be adding 3, and then 11 plus 3 is 14, 14 plus 3. So this here shows that we have a constant rate of change by adding 3 every time. And so that's a characteristic of a linear function. So linear function because there is a constant rate of change and I'll say of 3. Okay, so exercise 2. Find equations in standard form for each of the functions from exercise 1. Okay, so for table 1, we knew that this was an exponential function. So remember, exponential functions have standard form of y equals a times b to the x. And so what we need to figure out is what are a and b. Well, a is our y-intercept, and we can see from the table that our y-intercept is 0, 5. So that means that a is 5. And b is going to be my change, my times 2. We call that our growth factor. So that's going to be 2. And once I have those two values, all I need to do is plug them in for a and b, and there's my equation. Table 2 we knew was linear, and so we're going to do y equals mx plus b for any linear function. And again, the two things you need are the slope and the y-intercept. So we can see from the table, the change in y over the change in x is 3 over 1, or just 3. And my b is my y-intercept, which I can see from the table is 8. And so we put those values in to get a linear equation of y equals 3x plus 8. All right. It is interesting that linear and exponential functions are ones where 2 points on the curve will always determine the equation of the curve. So for exercise 3, we're going to consider the 2 points 0, 12, and 1, 3. Create a linear equation that passes through these sets of points in y equals mx plus b form, and an exponential equation in y equals a times b to the x form that also passes through them. Then, using your graphing calculator, graph both using a window of -2 to 2 for our domain and -5 to 15 for our range. Okay, so let's go ahead and I'm just going to split my screen here. So I'm going to say linear versus exponential. And so what they're saying is write the equation of a linear function that passes through the points 0, 12, and 1, 3, and then write an exponential function that passes through those same points. Okay, so if we were doing a linear function, remember the two things I need for a linear function are my slope and y-intercept. Okay, so in order to find the slope of the line that goes through those 2 points, I'm using my slope formula, y2 minus y1 over x2 minus x1. And so my slope, if I choose this as 12 minus 3 over 0 minus 1, I'm going to get that my slope is -9. Okay? If you needed to find your y-intercept algebraically, you could then take that and plug it into y equals mx plus b. So you pick a point and you plug it in along with the slope and you'd solve for b. But because I can see 0, 12 is the y-intercept, I don't need to go through all of that work. So my equation would be y equals -9x plus 12. Okay. For exponential, we know that our form is that. And so again, if I'm going through these 2 points, the first thing I need to know is what my a is, which again is your y-intercept of the exponential function. And we can see our first point is our y-intercept, so there we go. Okay, and then to get our b, which is our growth or decay factor, you have to think about, and sometimes I like to show this as a table. So if I know that these are my 2 points, okay, I have to think, well, how did I get from 12 to 3? Well, I divided by 4, but we don't use divided by when we talk about a growth or decay factor. We would say it was multiplied by 1/4. Okay, so our b would be 1/4. That's how I got from 12 to 3. 12 times 1/4 equals 3. So now I have the two things I need. Y equals 12 times 1/4 to the x power. And by the way, you could put 0.25 for your b. You don't have to use a fraction. Okay, so now what they're asking us to do is to create a graph to show what these two functions look like. And they've given us our window, which is really nice because I don't have to mess around with getting it to be perfect. So what I'd like you to do is to open up your graphing calculator, and you're going to open up a new graph page. And in your first function, f of 1, you're going to type in your line, the equation of your line. So -9x plus 12. You're going to press enter. Don't worry about if you can see it right now. We'll play with the window after. And then you're going to hit tab so that you can get another function in. And you're going to type in 12 times, and you could do 0.25 to the x power. So use your little caret key, and then to the x. Or if you want to put the 1/4, that's fine too. And then press enter. And then before we even go any further, let's go back in and change the window to what they're saying it needs to be. So once you're on your graph, you're going to hit Menu, Window Zoom, and then we're going to go to Window Settings. And for our x-min, we want to say -2 because they're saying our domain should go from -2 to 2. So -2 for x-min, +2 for x-max. And then we're going to go down to where it says y-min, and we're going to make that -5. And then we're going to go to y-max, and we're going to make that 15. Okay, so once you have that, you should be able to see a nice little graph here. And we're going to sketch that. So the one point I'm going to put on here is 0, 12 because they both share that point. So it kind of gives me a nice little place to kind of visualize where these are going. So I'm going to do my linear function first. So just based on what I see on my graph here. Oh, that's not good. Let me change that. Looks like my line is going to be something like this. And then for my exponential function, looks like it comes through something like that. That is really not perfect at all, but I'm going to go with it. Okay. And it's really just a way to kind of compare the two functions, so it doesn't need to be perfect. All right, let's go to the next page here. Recall that linear functions have a constant average rate of change, which we usually call slope. That's, of course, why they have a constant amount added for every constant change in x. Let's examine the average rate of change for an increasing exponential. So before we even look at example 4, think back to when we did quadratic functions. Okay, we were asked to find the average rate of change over some interval on a quadratic function. This is going to be done the same way. Okay, so because it's not a constant rate of change, we can't call it slope. Okay, we just call it average rate of change, but we still use our slope formula. Okay, so exercise 4 says the exponential function f of x equals 4 times 2 to the x is shown partially in the table below. Find the average rate of change over the various intervals given. This should be relatively simple because the change in x is 1. Okay, so the first interval we're looking at is when x is between 0 and 1. And so we're really using these 2 points right here. Okay, so just for this first one, I'll write them out. So we're using 0, 4, and 1, 8. That's what it means when they say the interval from 0 to 1. Okay, so if I do my slope formula, and remember we're not going to call it m because it's not slope, it's average rate of change, but I still do y2 minus y1 over x2 minus x1. And so for this particular interval, my average rate of change is 4. Okay, we could do the same thing for the interval from 1 to 2. So if I use those points, I'm looking at 1, 8 and 2, 16. So I do y2 minus y1 over x2 minus x1. And I get that the average rate of change between those 2 points is 8. Okay, let's keep going. So the interval 2 to 3, I'm using 216 and 332. So y2 minus y1 over x2 minus x1 gives me an average rate of change of 16. So you can probably start to see the pattern here. 332 and 464, y2 minus y1 over x2 minus x1. So that interval has an average rate of change of 32. Okay, so E says, what is clearly happening to the average rate of change as x gets larger? So we can see that the average rate of change went from 4 to 8 to 16 to 32. So clearly, it's doubling. So I'm going to say it is doubling as x increases by 1. Okay. The fact that the slope of an increasing exponential is always increasing has an interesting consequence. So exercise 5, consider the linear function y equals 20x plus 5 and the exponential function y equals 5 times 2 to the x. Both of these functions have a y-intercept of 5, so they start in the same location. So using your calculator, we're going to sketch these two curves on the axes below for the indicated window, and we're going to label each with its equation. Okay, so let's go ahead and clear out the graphs that you currently have in there. Okay, and let's go ahead and put our two new functions in. So our first function is y equals 20x plus 5. That's our linear function. And then we're going to hit tab and put in our second one, 5 times 2 to the x power. That's our exponential function. And then once you have those in, we're going to go to our window settings again. So menu, window zoom, window settings, and we're going to use the window that they show us on these graphs. Okay, so for our x-axis, it looks like they want us to go from 0 to 3. So our x-min should be 0 and our x-max should be 3. And then we're going to do our y-min as 0, and it shows they want our y-max to be 30. So once you have your picture of your graphs, we're going to sketch them out. And the reason why they have 5 here is because, remember, they said they share that same starting point, that same y-intercept. And so my line, I'm just going to sketch this out, should look something like that. And don't forget to label. Okay, and then we have our exponential function starting at that same y-intercept, but it kind of curves around like this. Okay, your sketch should look something like that. Now part B says, again, using your calculator, sketch these two curves on the axes below for the indicated window. So we're not going to change any of our functions. It's the same two functions, but all they're asking us to do is to change our window. Okay, so go back into menu, window zoom, window settings, and now we are going to change our x max to 6. So still have a 0 for the min, but 6 for the max. And then for our y min, we're going to keep that 0, but for our y max, we're going to make that 150. And so now what we've essentially done is we've zoomed out. And so you should be able to see now where those two functions intersect. Okay, so our linear function now kind of looks like this. And our exponential function still starts at that same y-intercept, but we can see that now it intersects our linear function. Okay. So part C says, although the line appears to rise more quickly than the exponential at first, the exponential eventually catches up and surpasses the linear. Why will an increasing exponential function always catch up with an increasing linear function? So just to kind of rephrase that, what they're saying is, in that first graph, it looked like our line was steeper. It looked like it was going to always be higher than our exponential was. But when we zoomed out, we could see that eventually that exponential curve overtook the linear, meaning it increased at a faster rate. And so they're asking us why this will always happen. Why will, no matter what, an exponential function will always surpass a linear function. And the reason is because it's increasing at a constant ratio versus a constant difference. Okay, so your line, you're just adding the same number every time, where in an exponential function, you're multiplying by the same number every time. And so if you think about that, it's always going to be faster when you're multiplying by some number than when you're adding a number. Okay, so that's how we want to explain this. So I'm going to say an exponential function will always surpass a linear function because the exponential function is increasing by a common ratio rather than a constant difference. So what's really cool about this, and I'm wondering if anybody picked up on it, is if you think back to when we learned about sequences and we talked about how an arithmetic sequence was when there was a common difference and a geometric sequence was when there was a common ratio. This is exactly what we were learning. Okay, so our arithmetic sequences were always some kind of a linear function, and a geometric sequence was always an exponential function. And so when we talk about common ratio versus common difference, it goes right back to sequences. So these two things, I'm hoping you can see the connection back to sequences, because that's exactly what this is, which is kind of cool. Okay, so for this next part, this is really just practice of what we just went over. So if you would like, you could pause the video and you could try these questions on your own, and then you could come back and check and see if you got them correct. Or if you're feeling a little bit, unsettled by what we just talked about, you can just listen and work through them with me. Okay? So number 1 says, for each of the following problems, a table of value is given where the change in x equals 1. For each, first determine if the table represents a linear function of the form y equals mx plus b, or an exponential function of the form y equals ab to the x, and then write its equation. Okay, so in A, let's look and see how our values are changing. So we can see in x, they are increasing by 1 every time, which they tell us that in the situation, so that's good. So then I want to see, okay, how are my y's increasing? Well, it's adding 3 each time. And so that is a characteristic of a linear function. Okay, so for a linear function, I need to write my equation in y equals mx plus b form, slope-intercept form. And so I need the slope and the y-intercept in order to do that. So because I can see my change in y over my change in x is 3 over 1, that means that my slope is 3. So I'm going to start by saying y equals 3x. And then I need my y-intercept, which looking at the table is this point right here. It's whenever x is 0. So I don't have any work to find that. Okay, in B, we have the same thing for our x. It's increasing by 1. And for my y, it looks like it's going up by 4 and then up by 12, so it looks like it's not linear. So let's see if I were to multiply. This is times 3, times 3. There we go. So our common ratio is times 3. So this is exponential. And the equation we use for this is a times b to the x. And so remember, a is your y-intercept, which we can see is 2. B is my growth factor, which in this case is 3 to the x power. Okay, for C, again, we're going up by 1 in our X. Perfect. If I go and I look at my Y values, I can see that for each of these, I'm dividing by 2, which is the same as multiplying by 1/2. So times 1/2 is now my decay factor, by the way, because it's going down. So we're going to say this is exponential. I can see right here my y-intercept is 8, so I know my a value is 8. And we just found my decay factor to be 1/2. So there we go. All right, in D, again, X is going up by 1. Y looks like we are subtracting 16. And that is constant, a constant difference, so this is linear. Okay, so I need my slope and my y-intercept. So my slope is the change in y over the change in x, which is just -16. So y equals -16x. My y-intercept right there on the table is 0, and so you don't have to write the +0. All right, for E, what's going on here? Let's see. So we know these are all going up by 1. All right, so I can clearly see that this is not linear because I'd be adding 4, then 5, and so on. So let's test if it is exponential. So in order to do this, I'm going to kind of work backwards. I'm going to see what is 20 divided by 16. And when I do that, I get 1.25. So I know 16 times 1.25 gave me 20. So let's test that. Is 20 times 1.25 25? Yes. Is 25 times 1.25 31.25? Yes. And then is 31.25 times 1.25 39 and 1/16? Yes. Okay, so this is exponential. And for our equation, I can see my y-intercept is 16. So 16 times my growth factor was 1.25 to the x power. All right, one more like this. So we're adding 1 for x. Okay, so for our y values, it looks like we are subtracting 20 every time. So we know that this is linear. All right, so our slope is going to be -20 over 1, or just -20. And my y-intercept is right here, 180. All right, exercise 2. The data shown in the table below represents either a linear or exponential function. Which of the equations below best models this data? Okay, so basically the same thing we were doing, we just have to then choose the correct equation. So let's take a look at the table. We can see x is going up by 1 every time, and it looks like we are doing times 2 for our y values. So immediately we know that this is going to be an exponential function, and so choices 3 and 4 are out, because both of those are linear. Okay, so then the next thing I'm going to look for is which of these choices shows a growth factor of 2, and they both do. So they both have a 2 for their growth factor. So what's going to be the determining factor here is what is the y-intercept. Now I can't see the y-intercept on the table, so I'm going to have to work backwards to figure that out. So I know that the next x value would be 0 if I go backwards. And so if I think about that for my y values, if I'm doing times 2 every time, what times 2 gives me 10? 5. So I know it has to be choice 1. Okay, we have our last page here. So number 3, wildlife biologists are tracking the population of albino deer in an upstate New York forest preserve. They record the population every year since 2005, which they consider to be time equals 0. Their data is shown in the table below. Okay, so because they started tracking in 2005, they're calling that year 0. 2006 is year 1, and so on. And then they have their population listed there. Okay, so part A says, although neither a linear nor an exponential function would model this data perfectly, justify why an exponential function would be a much better fit. Specifically, explain both why a linear function would not be a good fit, while an exponential would be reasonable. Okay, so if we think about populations in general, okay, typically populations take on an exponential curve because if you think about it, you have this, the offspring can reproduce. Okay, so if you have 86 deer, you think, okay, well, how many offspring would those 86 deer produce? And then you also have the offspring reproducing and their offspring reproducing and so on. So the population typically grows exponentially. Think back to 7th grade when you guys made tree diagrams, right? If we started with 2 deer at the top, okay, and then showed their offspring, and then off of those offspring showed their offspring, you would see that your population was growing very quickly, okay? This is a great application in the time that we're in with the coronavirus. This is exactly what happens is you have someone who has the virus, and then they spread it to 2 people, okay? And then those 2 people spread it to 2 people and so on. So it's definitely very applicable in our world right now, and it's really similar to this situation. Okay, so after all of that, let's say with population, an exponential function makes the most sense to use because as deer produce offspring, then those offsprings reproduce the population multiplies. And now it says we have to say something about why linear doesn't work. So I would say if it were linear, that change would be constant, which means only the newest deer would have offspring, which we know is not the case. Okay, so that just means like the babies have babies, not all the babies that came before. So if it were linear, the change would be constant, meaning only the newest deer would reproduce. And actually, it doesn't even have to be the newest deer. It could be the original 2 deer, right? Any one pair, which we know is not the case. Okay, so part B says, determine an equation for an exponential that models this data in the form P equals AB to the T power. Okay, so remember, P is the population, T is the time. So if we're talking exponential, looking back at the table, our A value, our y-intercept, was 86. So I'm going to say P equals 86. And then I'm looking for my growth rate here. So what I would do is I would divide 98 by 86, 111 by 98, 128 by 111, and let's see what we get for our growth factor. And remember, it's not going to be the same every time because they told us it wasn't a perfect fit. Okay, so if I do 98 divided by 86, I'm going to get 1.1. 111 divided by 98, 1.1. 128 divided by 111, and I'm getting 1.2. 147 divided by 128, 1.1. And 168 divided by 147. Okay, so since it seems like I'm getting 1.1 for most of these, I'm going to use that for my growth factor. So 1.1 to the t power. Okay, now it says to use your model to predict the population of deer in the year 2014. Okay, so if I were to continue this table all the way out to 2014, we could predict this. Now it says to use our equations, so let's do that. But the first thing we have to figure out is what is t in the year 2014. Okay, so if I just go back up here, 2011 would be 6. 2012 would be 7. 2013 would be 8. So 2014 would mean t is equal to 9. Okay, so in our model, we're going to say P equals 86 times 1.1 to the 9th power. Okay, and let's round this to the nearest whole number because remember we're talking about deer, so we don't want to have, a fraction of a deer. And so I'm going to get 203 as my estimated population in 2014. All right, number 4. You can determine the equation of a line or the equation of an exponential given any 2 points that lie on these curves. In this exercise, we will pick 2 special points. Consider the points 0, 5, and 1, 15. So we did this on the other page. This is very similar to that example. And so for us to write an equation of a line that goes through those 2 points, the first thing I need is the slope. So I'm going to do y2 minus y1 over x2 minus x1. So I'm getting that the slope would be 10. The y-intercept is given to me. 0, 5 is the y-intercept, so b is 5. So the equation of the line that goes through those 2 points is y equals 10x plus 5. Now if I use the same 2 points, but I'm looking for an exponential, which is part B, the first thing I need is my a, which again is my y-intercept, which is 5, and my b is my growth factor. So if I look at a little table here of my 2 points, 0, 5, 1, 15, I can see that I multiplied by 3 to get that, and so my growth factor is 3. So y equals 5 times 3 to the x power. All right, and then we're going to put these in our calculator and we're going to sketch the 2 graphs. So you can see the window they want you to use here. So let's go in, new graph, first function, y equals 10x plus 5, tab, put in our second function, 5 times 3 to the x, press enter. Let's go into our window settings, so menu, window zoom, window settings. Our x-min, they want us to be at -3. Our x-max is +3. Our y-min is -10. And our y-max is 30. Okay, just like on the other example, I'm actually going to put 5 right here because that's that common point that they share. Okay, so if I sketch out what I see on my calculator, you can see my linear function looks something like this. And it looks like my exponential function looks like something like that. Increase was a little dramatic, but It's just a sketch. All right. Great job. That was a long lesson, so thank you for sticking with me.